Hi class. In this video here we want to continue talking about applications of differentiation by now beginning our discussion of concavity, and then we'll move into something called the second derivative test at the end of this section or this lecture. Okay, so what are we going to be covering in this section, or what we're going to work on? So this is going to be like the previous section, a pretty long section with a lot of materials, so I'm going to break it up into multiple videos. Okay, so the first thing we're going to do is we're going to talk about how you determine intervals on which a function is what we call concave upward or concave downward. I'll explain what that is. Okay, so this is going to be lecture video number 1. Then what we're going to talk about is how you find points of inflection of the graph of a function, and I'm going to break that up into lecture video number 2. And then the last thing we're going to talk about in this section is how you apply the second derivative test to find relative extrema of a function. So those relative extrema are the max-min values of a function. So we talked about how you did this with the first derivative test and in the previous section, but now we're going to employ this thing called the second derivative test to do this. And I'll do this in a third lecture video. So it'll be all nice broken up for you here. All right, so let's talk about concavity. All right, what exactly is concavity? So let's let f be differentiable on some open interval I. Okay, the graph of f is what we call concave upward on I if f prime is increasing. So that means the derivative is increasing. So the slope of the tangent line is increasing, all right, on that interval. And the graph is concave downward on I when f prime is decreasing on the interval. So that means the slope of the tangent line is decreasing. Okay, so just kind of like some, breaking this down a little bit, a function is what we call concave upward, where its derivative is increasing. All right, a function is concave downward, where its derivative is decreasing. So just so you can see what exactly this means here. All right, so here are two graphs. The one on the left here is a graph of a concave upward function. Okay, so you can see here, this blue is the tangent line. And look, the tangent line is, as x increases, the graph, the slope of the tangent line is increasing. So it's turning leftward in, okay? You can see it there. Okay, that's what it means to be concave upward. Now here's concave downward. It's actually the flip of the graph here. Right? You can see that the slope of the tangent line, the blue tangent line when it comes back here, starts really steep, and then it falls, and then at some point it actually turns and becomes negative. But that would be concave downward, where the slope of the tangent line is decreasing. All right, so concave upward, just so we're clear, f prime is increasing. Concave downward, what it means is f prime is decreasing. So how we find concavity? So we used the first derivative of a function, okay, to find where it's increased, where a function is increasing or decreasing. So let me just go back a slide here, right? We're looking for where f prime is increasing, right? So we're looking at its rate of change. So the rate of change of the first derivative is just the second derivative. Same thing over here. We're looking where f prime is decreasing while we're looking at its rate of change. So that's just the derivative of the first derivative. So we're going to look at the second derivative for this. Okay, so this is how we're going to test for concavity. Let's let f be a function whose second derivative exists on an open interval I. All right? If f double prime of x is greater than 0 for all x in I, then the graph of f is concave upward on that interval. If f prime of x is less than 0 for all x in I, then the graph of f is concave downward on I. Okay, so this is important down here. I wrote, what the key points here. Okay, the sign of the second derivative is a test for concavity. Okay. If f double prime is greater than 0, then f prime is increasing, so the slopes of the tangent line increases as you go left to right. Likewise, if f double prime of x is less than 0, then those slopes of the tangent line are decreasing, all right, as you go left to right. And you can see that in both of these graphics here. Okay. So what we're going to do here, all right, how we're going to find intervals. So to find intervals of concavity, it's going to be a very similar process. Very, very similar process to finding intervals of increasing, decreasing. Very, very similar. So what we're going to do, all right, is we're going to start, all right, we're going to start by finding when f double prime of x is equal to 0. And then we're going to use those values right there to carve up an interval to test for concavity. Okay. And so, what you're going to notice with some of these examples over the coming lectures is, finding the second derivative, if it's a polynomial function, is pretty easy. But then I'll do an example with a rational function, and maybe it's not so easy. All right. So here's what we want to do. For the following function, let's determine an open interval on which the function is concave upward and then where it's concave downward. All right, so here's going to be our function. We'll start with a nice polynomial function. F of x is equal to x to the fourth minus 3x cubed. Okay, so looking back, to do this, what we're going to need to do is we're going to need to find the second derivative. That's the first thing we're going to do. So f prime of x, we'll find the first derivative. This is 4x cubed minus 9x squared. And now we're going to take the derivative of that. So the second derivative, so the derivative of the derivative. This becomes 12x squared minus 18x. Okay, so now what you're going to do, you're going to set f double prime of x equal to 0, and you're going to solve. So f double prime of x is equal to 12x squared minus 18x. So you're going to solve by factoring here, right? So you can factor out a 6x. When you do that, you're left with 2x minus 3 is equal to 0. So then it's very simple to see here. You're going to use the zero product principle, right? So either 6x is equal to 0 or 2x minus 3 is equal to 0. So you have x is equal to 0, just divide by 6. Here, add 3 over, divide by 2. You have another x value as x is equal to 3/2. Okay, so to start, how are you going to know what intervals? Well, you have to look at the domain of this function, right? So the domain, because it's a polynomial function, goes from negative infinity to infinity. So all you're going to do is you're going to use the endpoints of the domain and these values you found here where the second derivative was equal to 0. And then what you're going to now do, set up a table, okay, to help find the intervals, or to help solve. And what I mean by here is you're going to do this just like you did with the tables for increasing or decreasing. All right, so you're going to start with your intervals. Well, it looks like you're going to go from negative infinity to 0. Then you're going to pick up and go from 0 to 3/2. And then you're going to go from 3/2 to infinity. A little bit of a typo there. 3/2 to infinity. Now what you're going to pick is you're going to pick a test value inside the interval. So pick something very easy, right? Between 0 and negative infinity, I'll pick -1. Between 0 and 3/2, I'll pick 1. Between 3/2 and infinity, I'll pick 2. And now all you're going to do is you're going to look at the sign of f double prime of x evaluated at each of these test values. Okay, so this is our second derivative, okay? It's 12x squared minus 18x, okay? So f double prime evaluated at -1, well look, this becomes 12 minus 18 times minus 112 plus 18, this becomes 30, so it's greater than 0. F double prime of 1, if you plug 1 into this, you get 12 minus 18, so that's less than 0. And now f double prime of 2, right, 2 squared is 4, 4 times 12 is 48, minus 18 times 2 is 36, so this is positive. All right, so then what is our conclusion? Okay, so wherever it's greater than 0, that means it's concave upward. So it's upward here. And whenever the sign is less than 0, that means it's concave downward. So just what we can say is this graph is concave upward on negative infinity to 0 and 3/2 to infinity, and that it's concave downward on this middle interval, 0 to 3/2. Okay, not too bad. So basically what you're doing, okay, and hopefully you can see here, what you're doing is you're doing the same exact procedure you did for increasing or decreasing, but what you're doing now is you're looking at the second derivative, okay, and you're applying the same concepts to it. All right, let's do another one here as another example for this lecture video here. We'll do a rational function here. Okay, so our function is going to be this. F of x is equal to x plus 8 divided by x plus 7. All right, so just looking at this, right? So, it's very easy to see that the domain here was all real numbers. So for this problem here, the domain, what you can't have, right? You can't have a divide by 0. Okay, so the domain here is x such that x is not equal to -7. Let me actually change this. I'm going to make this x minus 7 instead of x plus 7. So then, sorry about that. So then we can just see here that x is not equal to 7. All right, so that means my domain would also be negative infinity to 7 union with 7 to infinity. All right, changing that to x minus 7 there. Sorry about that. All right, so here's the process. We need to find the second derivative. All right, so we've got to find the first derivative first. Okay, and you're going to need the quotient rule. All right, it's the derivative of the numerator, which is just going to be 1, times the denominator, x minus 7, minus the numerator times the derivative of the denominator, which is just 1, all over the denominator squared. Okay, so let's clean this up a little, right? So this just becomes x minus 7, and then distribute the negative minus x minus 8 all over x minus 7 squared. Well, look, x's cancel out, right? X minus x, so this just ends up being minus 15 all over x minus 7 squared. And actually, to help us find this is going to be really easy now to find the second derivative, I'm going to write this as negative 15 times x minus 7 to the negative 2 power. So then our second derivative here, minus 15. I'm going to need to chain rule this. Okay, I'm going to bring the negative 2 down, times x minus 7, and then minus 2 minus 1 becomes minus 3. And then the derivative of the inside here is just 1, actually. So this right here becomes, let's see, negative is positive, so this is 30 over x minus 7 cubed. Okay, so what's really interesting now, okay, is this, you notice, okay, f double prime of x, it can never be equal to 0. There's actually no way you can pick a value such that it's equal to 0. So so the next part, it's kind of like, whoa, then how do I set up the intervals? If there's no 0 here, well, then what you do is you're just going to use the domain. Okay, so use the domain up here as your intervals. And that's okay. That's okay. So it's actually pretty easy. All we have to do is test 2 intervals here. So what I'm going to do is I'm going to go to the next slide here, and I'm going to rewrite our second derivative so you can see it. And what you also have to notice here as you do this, okay, is if you make one little error and have an x somewhere in there, it's going to throw off everything okay? So like maybe, you know, if you made a mistake and wrote this as 2x instead of having them cancel out, then it's like you're going to make a mistake. So you have to be very, very meticulous as you find these derivatives. All right, so our second derivative was this. And our domain here was negative infinity to 7 and 7 to infinity. So we're going to use our domain as the intervals. We're going to pick a test value in these intervals. You can pick any number. I'm going to pick 0, and then I'll pick 8 here. And now look, you're going to look at the sign of f double prime of x. Well, f double prime of 0. If you plug 0 in here, remember, you're only interested in the sign. This is 0 minus 7 is minus 7. Minus 7 cubed is a negative number. Positive divided by a negative. Negative. And then f double prime of 8. Well, 8 minus 7 is 1. 1 cubed is 1. 30 divided by 1, positive. All right, so our conclusion here is that here it's concave downward, and here it's concave upward. So the graph is concave upward, or excuse me, I'll start with downward, concave downward on negative infinity to 7. And then it's concave upward on 7 to infinity. And we're going to do more of these examples. We're going to, in the next video lecture here, what I'm going to do is I'm going to talk about points of inflection. And you're going to see that's where it's going to change from something being concave downward to concave upward. And in this case, not because you're actually up against the vertical asymptote, but in other cases, we're going to redo this whole procedure. So we're going to get more examples of these intervals, and we're just going to expand on it. So we'll continue that in the next lecture.